Flight Lieutenant James "Ginger" Lacey's Supermarine Spitfire shuddered as he threw it into another climbing turn over the English Channel. September 15th, 1940. The sky above Dover was a chaos of contrails and tracer fire. Below him, 3 Messerschmitt Bf 109s were climbing fast, their yellow noses cutting through the morning haze like sharks rising from the depths. Lacey had been flying Spitfires for 8 months now, and he knew exactly what was about to happen. The 109s had altitude advantage and superior climbing performance. In about 30 seconds, they would be above him with the sun at their backs, and he would be fighting for his life at a disadvantage. It was the same story that had played out dozens of times since the Battle of Britain began. The Messerschmitt could outclimb the Spitfire. Every British pilot knew it. Every German pilot exploited it. His instrument panel told him everything he already knew. Airspeed, 280 miles per hour. Altitude, 18,000 feet. Boost pressure, plus 6 pounds. That boost pressure was the critical number, the limit that Rolls-Royce engineers had drilled into every pilot's head during training. Never exceed plus 6 pounds of boost. The Merlin engine in your Spitfire is precision-built, finely tuned, and absolutely cannot handle more pressure than that. Push it harder and you'll blow the engine, seize the cylinders, destroy £12,000 worth of irreplaceable British engineering, and probably kill yourself in the process. Lacey watched the 109s closing the altitude gap, 1,500 feet, 1,200 feet. In maybe 20 more seconds, they would be in position to dive on him, and he would have to break off his attack on the German bomber formation he had been stalking. Another failed intercept. Another day of watching German aircraft pound London while British fighters struggled to stop them. Then Lacey did something that every instructor, every engineering officer, and every manual had explicitly forbidden. He reached down and shoved the throttle lever forward, past the plus 6 pound gate, past the stop that was supposed to prevent exactly what he was doing, all the way to the emergency override position. The boost pressure gauge needle swung violently to the right, plus 12 pounds, double the rated maximum. The Merlin engine's roar changed pitch, rising from a steady howl to a screaming crescendo that Lacey could feel through the entire airframe. The Spitfire leaped forward like a racehorse given the whip. The rate of climb indicator spun upwards so fast it momentarily pegged at the top of its range, and suddenly, impossibly, Lacey was climbing faster than the Messerschmitts below him. The German pilots saw it too. Lacey watched their formations waver, break, as they realized the Spitfire they had been confidently hunting was now above them, diving down with guns blazing. His 8 Browning machine guns converged on the lead 109. The German fighter rolled desperately, but too late. Lacey's burst caught it along the fuselage, and the 109 began trailing white smoke. Its coolant system ruptured. When Lacey finally throttled back and the Merlin settled into its normal roar, he waited for the catastrophic failure he had been promised would happen, waited for the engine to seize, for oil pressure to drop, for the grinding sound of destroyed bearings and broken pistons. But the Merlin just kept running, smooth and powerful, as if nothing unusual had happened. What Flight Lieutenant Lacey didn't know as he turned for home with his first kill of the day was that he had just stumbled onto a secret that would change the entire Battle of Britain. A mistake made months earlier by a Rolls-Royce engineer, buried in paperwork and overlooked during the chaos of wartime production, had given British fighters a hidden capability that nobody knew existed. And within weeks, what began as one pilot's desperate rule-breaking would become standard operating procedure that would help save Britain from invasion. This is the story of how a tuning error transformed the Spitfire from an aircraft struggling to match German performance into a fighter that could dominate the skies over England. It's the story of innovation born from desperation and miscommunication, and how the laws of thermodynamics and metallurgy proved more forgiving than the engineers who designed the Merlin engine had believed possible. To understand why Lacey's discovery was so revolutionary, you need to understand just how precarious Britain's position was in the summer and fall of 1940. The Luftwaffe had swept across Europe with devastating effectiveness. Polish, French, Belgian, and Dutch air forces had been crushed in weeks. German fighter tactics, honed during the Spanish Civil War, were considered the most advanced in the world, and the Messerschmitt Bf 109E was, by every measurable standard, one of the finest fighter aircraft ever built. The 109E could climb to 20,000 feet in just over 7 minutes. The Spitfire Mark I required nearly 9 minutes for the same climb. In fighter combat, 2 minutes might as well be an eternity. It meant that German fighters could always dictate the terms of engagement, choosing when and where to attack, climbing above British fighters and diving down with the sun behind them. The performance gap wasn't massive, but it was consistent and exploitable. German pilots, many of them veterans with hundreds of hours of combat experience from Poland, France, and Spain, knew exactly how to use their advantage. They would climb above British formations, wait for the optimal moment, then dive at tremendous speed, fire a burst, and climb back to altitude before the Spitfires could react. It was called boom and zoom tactics, and it was devastatingly effective. British pilots were dying, not in massive numbers, but steadily, relentlessly. Fighter command was losing aircraft and pilots faster than they could be replaced. Air Chief Marshal Hugh Dowding, commanding fighter command, could see the mathematics of the battle turning against him. Every day, German bombers struck British cities and airfields. Every day, British fighters rose to intercept them. And every day, the Luftwaffe had a slight but measurable performance advantage that was grinding fighter command down through sheer attrition. The Spitfire was a magnificent aircraft, perhaps the most beautiful fighter plane ever designed. Reginald Mitchell's masterpiece featured elliptical wings that gave it unmatched maneuverability and elegant lines that made it instantly recognizable. But beauty doesn't win battles, and the Spitfire's Rolls-Royce Merlin III engine was rated at 1,030 horsepower at plus 6 pounds of boost pressure. The Messerschmitt's Daimler-Benz DB601A engine produced 1,175 horsepower using fuel injection and direct drive supercharging. That 145 horsepower difference translated directly into climbing performance, and climbing performance was the coin of the realm in 1940 air combat. Altitude meant life. Altitude meant you chose when to fight. Altitude meant you could dive away if the engagement went badly, using gravity and speed to escape. Without altitude advantage, British pilots were fighting at a disadvantage every single time they took off. The Rolls-Royce Merlin engine was a masterpiece of engineering, a liquid-cooled V12 that represented years of development and refinement. Every component was machined to exacting tolerances. The supercharger was carefully calibrated to provide maximum boost without exceeding the structural limits of the engine block, pistons, and connecting rods. The fuel mixture was precisely tuned to prevent detonation, the catastrophic pre-ignition that could destroy an engine in seconds. And critically, Rolls-Royce engineers had set the maximum boost pressure at plus 6 pounds for a very specific reason. They had tested the Merlin extensively, and they knew that at higher boost pressures, the risk of detonation increased dramatically. Pre-war aviation fuel simply couldn't handle the temperatures and pressures generated by higher boost settings. Push the engine too hard, and the fuel-air mixture would ignite prematurely before the piston reached the top of its compression stroke. The resulting shockwave would crack pistons, bend connecting rods, and destroy the engine within minutes or even seconds. The plus 6 pound limit wasn't arbitrary caution. It was based on solid engineering data using the 87-octane fuel that British aircraft had been using for years. Exceed that limit and you were gambling with your life. But what nobody realized, what even Rolls-Royce engineers didn't fully understand in the chaos of 1940, was that the fuel had changed. In late 1939, as war became inevitable, Britain had secured contracts for large quantities of aviation fuel from American suppliers. The specifications called for 87-octane fuel, the standard grade that British aircraft had always used. But American refineries, using different crude oil sources and more advanced refining processes, were producing fuel that consistently tested at 100 octane or higher. The higher octane rating meant the fuel could withstand significantly more compression and temperature before detonating. It was better fuel, more resistant to pre-ignition, capable of supporting higher boost pressures without the catastrophic detonation that lower octane fuel would suffer. But nobody told the pilots. Nobody recalibrated the boost pressure limits. Nobody revised the operating manuals. The mistake compounded during engine production. At the Rolls-Royce factory in Derby, a production engineer named Stanley Hooker was overseeing the installation of new fuel flow meters in Merlin engines destined for Spitfire production. Hooker was brilliant, a Cambridge-trained mathematician who would later become one of Britain's most important jet engine designers. But in March 1940, working 18-hour days to meet production quotas, he made a simple calibration error. The fuel flow meters were supposed to limit maximum fuel delivery to match the plus 6 pound boost rating. Hooker, reading from a chart that had been updated to reflect the new American 100-octane fuel, but working with installation specifications written for 87-octane fuel, calibrated the meters to allow significantly more fuel flow. It was an honest mistake, the kind of error that happens when multiple specifications are being updated simultaneously during wartime production chaos. Nobody caught it. The quality control inspector who should have verified Hooker's work was sick that week, his duties covered by a replacement who didn't know what numbers to look for. The engines passed inspection, were installed in Spitfires rolling off the production line at Castle Bromwich and Eastleigh, and were delivered to frontline squadrons throughout the spring and summer of 1940. Pilots were still being told never to exceed plus 6 pounds of boost, but the engines they were flying could actually handle much more. The combination of 100-octane fuel and Hooker's calibration error meant that these Spitfires could run at plus 12 pounds of boost, generating nearly 1,400 horsepower without suffering the detonation and mechanical failure that would have destroyed engines running on 87-octane fuel. The capability was there. The pilots just didn't know it existed. Flight Lieutenant Lacey's decision to push past the boost limit on September 15th was pure desperation. He had been in combat almost daily since early August. He had watched friends die, watched bombers get through to London because British fighters couldn't climb fast enough to intercept them. He was exhausted, frustrated, and in that moment over Dover, he simply decided that if he was going to die, he might as well die trying something instead of following rules that weren't working. He survived. His engine survived. And when he landed at his base at Biggin Hill and shut down the Merlin, the ground crew couldn't find anything wrong with it. Oil pressure was normal. Coolant temperature was normal. There was no sign of the catastrophic damage that should have occurred. Lacey didn't report what he had done, not officially. You didn't admit to deliberately violating critical operating procedures, not if you wanted to keep flying. But that evening in the pilot's mess, he mentioned it quietly to his flight commander, squadron leader Michael Robinson. Robinson was an experienced pilot and a good commander who knew his pilots were struggling against better performing German fighters. Robinson listened to Lacey's story, thought about it for a long moment, then said something that would change British fighter tactics for the rest of the war. "Tomorrow morning, I want you to do it again, deliberately this time. I want to know exactly how long the engine can sustain that boost level and exactly how much performance improvement we get." The next day, September 16th, Lacey took off on a training flight with specific instructions to test the limits of his Spitfire's engine. He climbed to 10,000 feet, pushed the throttle past the plus 6 pound gate to maximum boost, and started his stopwatch. The Merlin screamed. The Spitfire accelerated and climbed like it had never done before. Lacey held maximum boost for 5 minutes, the entire time expecting catastrophic failure. Nothing happened. He throttled back, let the engine cool, then tried again. Same result. The engine was running hot, definitely working harder than it was designed for, but it wasn't failing. He landed with data that Robinson could barely believe. At plus 12 pounds of boost, the Spitfire could climb to 20,000 feet in 6.5 minutes. It was faster than the Messerschmitt 109. Robinson immediately contacted the engineering officer at Biggin Hill, squadron leader David Evans. Evans was skeptical, certain that this had to be a mistake, or that the engine would fail catastrophically with just a few more hours of operation. He ran his own tests on Lacey's aircraft, measuring temperatures, pressures, and structural stresses. Everything was running hot and hard, but within parameters that suggested the engine could sustain this level of performance, at least for short periods. Evans didn't understand why it was working, but he couldn't deny the data. He contacted Rolls-Royce directly, asking for clarification on boost limits given the new 100-octane fuel that had been in use for months. That inquiry eventually reached Stanley Hooker, who looked at his production records, checked his calibration notes, and realized what had happened. His mistake had actually created engines that were perfectly tuned for the 100-octane fuel Britain was now using. The fuel flow meters he had calibrated were allowing exactly the right amount of fuel to take advantage of the higher octane rating without causing detonation. What Rolls-Royce had thought was the absolute maximum safe boost for Merlin engines running on 87-octane fuel was actually a conservative limit that left significant performance on the table when using 100-octane fuel. Hooker immediately began running tests at the Derby factory. By the end of September 1940, Rolls-Royce had confirmed what frontline pilots were discovering through experimentation. The Merlin III engine, when using 100-octane fuel and properly calibrated fuel flow, could safely run at plus 12 pounds of boost for up to 5 minutes at a time. This emergency boost setting increased power output from 1,030 horsepower to approximately 1,400 horsepower. The improvement was staggering, a 36% increase in power output with no hardware changes, just a recalibration and a revision to operating procedures. Spitfires that had been struggling to match German climb performance could now outclimb the Messerschmitt 109E. The tactical situation was about to reverse completely, but there was a problem. Fighter Command had hundreds of Spitfires in service, and they weren't all equipped with Hooker's miscalibrated fuel flow meters. Some had the old meters calibrated for 87-octane fuel, and those engines really would fail catastrophically if pushed past plus 6 pounds of boost. There was no easy way to tell which aircraft had which meters without pulling the engines and inspecting them directly. The solution came from an unexpected source. Sergeant Frank Whittle, a ground crew chief at RAF Hornchurch, had a brother who worked at the Rolls-Royce factory. Through informal communication, Whittle learned about Hooker's calibration error and the production dates when the new meters had been installed. He cross-referenced production dates with the serial numbers of engines at his base and created a list of aircraft that could safely use emergency boost. Whittle's list was copied and shared across Fighter Command through unofficial channels. Engineering officers at bases throughout southern England began checking their own aircraft serial numbers and creating similar lists. By early October, most frontline squadrons knew which of their Spitfires could safely use the emergency boost setting and which couldn't. The tactical impact was immediate and dramatic. German pilots who had been confidently using their climb advantage suddenly found British fighters climbing above them. Messerschmitt formations that had previously dictated the terms of engagement now faced Spitfires with altitude advantage and the tactical initiative. Squadron leader Douglas Bader, commanding 242 Squadron, was one of the first to develop tactics specifically designed to exploit the emergency boost capability. Bader was aggressive to the point of recklessness, a pilot who had overcome the loss of both legs in a pre-war flying accident to become one of Fighter Command's most effective leaders. Bader's tactics were simple and devastating. When radar detected incoming German formations, he would lead his squadron into a maximum rate climb using emergency boost from takeoff. The Spitfires would scream up to altitude, their Merlin engines howling at power levels that officially didn't exist, and position themselves above the German fighters before the Luftwaffe even realized they were there. Then Bader would dive, using gravity and speed to close with German bombers while the escort fighters were still climbing to engage. His squadron would make one devastating pass through the bomber formation, shooting down 2 or 3 aircraft, then use their remaining speed to zoom back up to altitude before the German fighters could react. It was boom and zoom tactics, the same technique the Luftwaffe had been using against British fighters for months, but now the tables were turned. The kill ratios began to shift. In August 1940, before the discovery of emergency boost capabilities, Fighter Command was shooting down approximately 1.2 German aircraft for every British fighter lost. By late October, with emergency boost procedures widely adopted, that ratio had improved to nearly 2-to-1 in Britain's favour. The Luftwaffe was still a formidable opponent, but it was no longer winning the war of attrition. German intelligence struggled to understand what had changed. Luftwaffe commanders knew that British fighters were suddenly performing better, climbing faster, and fighting more aggressively. They assumed Britain must have introduced a new version of the Spitfire with a more powerful engine. German photo reconnaissance aircraft were tasked with photographing British airfields to identify any new aircraft types. They found nothing because there was nothing to find. The Spitfires were exactly the same aircraft they had been fighting for months. They were just being flown differently. The physiological effects of using emergency boost were significant but manageable. Running the Merlin at maximum power generated tremendous heat. Cockpit temperatures would soar, particularly during prolonged climbs. Pilots learned to open their canopies slightly to let in cooling air, accepting the buffeting and noise in exchange for tolerable temperatures. The engines also required more maintenance. Running at plus 12 pounds of boost for even short periods put tremendous stress on every component. Spark plugs fouled faster. Oil needed to be changed more frequently. Pistons and bearings wore out more quickly. An engine that might normally go 200 hours between major overhauls now needed attention after 150 hours or less. But maintenance issues were manageable problems. Dead pilots and destroyed aircraft were not. Ground crews worked longer hours, performed more frequent inspections, and stockpiled spare parts to keep their squadrons operational. The Royal Air Force had always excelled at logistics and maintenance, and the ground crews adapted quickly to the higher maintenance demands. Rolls-Royce moved rapidly to formalize what had been discovered through accident and experimentation. By November 1940, all new Merlin engines were being produced with fuel flow meters calibrated for a 100-octane fuel and emergency boost capability. Retrofit kits were manufactured for older engines, allowing them to be upgraded in the field. Operating manuals were revised to officially authorize emergency boost settings of plus to 12 pounds for up to 5 minutes during combat. The company also began developing improved versions of the Merlin specifically designed to take advantage of high-octane fuel. The Merlin XX, introduced in 1941, was engineered from the start to operate at higher boost pressures, with strengthened components and improved cooling. It would eventually produce over 1,500 horsepower at war emergency power settings. Stanley Hooker, whose calibration error had started the entire chain of events, became a critical figure in British engine development. He went on to design the supercharger systems for later Merlin variants and eventually became chief engineer at Rolls-Royce. After the war, he would play a key role in developing Britain's first jet engines, but he always maintained that his most important contribution to the war effort was the mistake he made in March 1940 while installing fuel flow meters. The tactical and technical lessons from the emergency boost discovery spread throughout the Royal Air Force and eventually to Allied air forces. American pilots flying Merlin-powered P-51 Mustangs later in the war benefited directly from British experience with emergency boost procedures. The Packard-built Merlin engines in American aircraft were designed from the start to handle high boost pressures, and P-51 pilots routinely used war emergency power settings to chase down German jets and high-altitude bombers. The Battle of Britain is remembered as a triumph of British determination and fighter pilot courage, and rightly so, but it's also a story of technical innovation and adaptation under pressure. The discovery that Spitfires could safely use emergency boost came at exactly the right moment, when fighter command was being ground down by attrition and German performance advantages seemed insurmountable. Flight Lieutenant James Lacey, the pilot who had first broken the rules and pushed his Spitfire past its supposed limits, survived the Battle of Britain and the entire war. He was credited with 28 confirmed victories, making him one of Britain's highest-scoring fighter aces. In post-war interviews, he always insisted that his decision to use emergency boost that day over Dover wasn't courage, it was desperation. He was simply tired of losing, tired of watching German fighters outperform his Spitfire, tired of following rules that weren't working. Lacey retired from the RAF in 1967 as a squadron leader. He died in 1989 at age 72. Among his personal papers, his family found a letter from Stanley Hooker, written in 1975, thanking Lacey for being brave enough to discover what Hooker's mistake had made possible. The two men had never met during the war, but Hooker had tracked Lacey down decades later to tell him that his desperate rule-breaking had validated work that Hooker had thought was a career-ending error. The story of the emergency boost discovery is less well known than other Battle of Britain narratives, but it reveals something important about how wars are actually won. The Spitfire didn't suddenly become a better aircraft in September 1940. The Messerschmitt 109 didn't suddenly become worse. What changed was understanding, the recognition that the tools British pilots had been given were more capable than anyone realized. Today, restored Spitfires still fly at air shows around the world, their Merlin engines still producing that distinctive roar that defined the sound of British resistance in 1940. Occasionally, with special permission and strict safety protocols, pilots will push those restored engines to emergency boost settings, and the Spitfire will leap forward with the same dramatic surge of power that surprised German pilots over southern England more than 80 years ago. At the Royal Air Force Museum in London, there's a display featuring a Merlin III engine cut away to show its internal components. Next to it, a placard explains the emergency boost procedures that were developed during the Battle of Britain. The display mentions Stanley Hooker's calibration work and Flight Lieutenant Lacey's combat testing, but it doesn't use the word mistake. Official RAF history prefers to describe it as a fortunate calibration decision. Perhaps that's fair. In engineering, as in warfare, the line between mistake and innovation often depends on the outcome. Hooker calibrated fuel flow meters using specifications meant for fuel his engines weren't supposed to be using yet. That could have been a disaster if the new fuel hadn't arrived or if its octane rating had been lower than expected. Instead, it created a capability that helped change the course of the Battle of Britain. The lesson extends far beyond aviation history. Sometimes the most important innovations come from accidents, from mistakes that reveal possibilities nobody had considered. Sometimes the rules that seem ironclad and unbreakable are actually based on assumptions that are no longer valid. And sometimes changing the outcome of a conflict requires not better equipment, but simply understanding how to use the equipment you already have. The Luftwaffe dominated the skies in the summer of 1940 because German pilots had better tactics and the Messerschmitt 109 had better climb performance. British pilots were brave and determined, but bravery alone doesn't overcome physics and engineering. The Spitfire needed to perform better, and for months nobody knew it could. Then one engineer made a mistake, and one pilot was desperate enough to break the rules, and suddenly everything changed. The Spitfire didn't become a different aircraft. It became the aircraft it had always been capable of being if only someone had known to push it past the limits that everyone thought were absolute. That's the real story of how Britain held off the Luftwaffe during the Battle of Britain. Not just courage and determination, though those were essential. Not just superior radar and fighter control systems, though those made a crucial difference. But also a willingness to question assumptions, to take risks, and to discover that sometimes the tools you have are better than you think they are. All it takes is someone desperate or curious enough to find out what happens when you push past the limits everyone says cannot be broken. Sometimes those limits are real, and breaking them leads to disaster. But sometimes, just sometimes, they're not limits at all. They're just the edges of what we thought we knew, waiting for someone brave enough to step beyond them and discover what's actually possible.